So my talk will be about how to learn over dirty data, data with systematic errors like missing data directly from that without any cleaning or repairing your data. So to give some context, we know that data preparation is really important for machine learning and AI, but it's very expensive. We know that data scientists or AI engineer spend almost 80% of their time on preparing data, right? And what I mean by preparing data is that, okay, usually the data that we have has some systematic errors, missing data, inconsistent data. For example, this data set that we have is it's a data set about some features on cities, temperature, humidity, and we like to predict whether it's going to rain or not, right? And this has some errors. So I have missing values in some samples. I have negative humidity in other samples. So there are inconsistency and missing values in my data. And how I repair it actually will influence the model I learn. If I repair them correctly, if I repair my data correctly, I may learn the correct model, right? But if I do it incorrectly, I may get incorrect model because I have changed data in a way that doesn't really represent the true population. Okay, what are the existing methods of dealing with these sort of dirty data, as I mentioned? The first idea is just delete them, right? And so if I have this data set that has some samples with missing values or inconsistent values, I'm just going to delete them. And of course, it's not really the best way to deal with the problem because we're going to lose valuable information and might introduce some bias to my data. Another approach is to do data cleaning, data imputation, data repair. In that, I'll be using an expert if my data, my domain, my task is very sensitive. I'm going to use a pre-trained model to impute my data and find the right value, right? The repair data will be data that has the right value, the correct values for the data items I have in my original data set. Well, that will give me a clean, valuable, and reliable high-quality data set, but it's very costly. It's very costly in many domains to find experts. It might be costly to train the models that may impute the data if you're going to use model-based imputation. And often it's also not clear whether the data set that we get, finally the repaired data set, is accurate, right? It will depend on the process of data imputation, data cleaning. So what we suggest is to figure out when we can learn accurate models without cleaning dirty data. So something like this. So we get a raw training data, we check if it's dirty or not, and whether the dirty data is actually influential to the model I'm learning. So if it's influential to the model I'm learning, then I'm going to ask some expert or I'm going to use some pre-trained model to repair the data. Otherwise, we're going to just learn our model directly over the dirty data set, okay, which obviously will save a lot of basically resources and costs for data cleaning. So how can we figure out whether we need to clean our data or not, right? First, I'm going to define a repair as a sort of a complete data set where we have imputed, we have replaced every missing or data values with some arbitrary data value, right? So these repairs need not to be correct or accurate repair of my data, right? And obviously every dirty data set, every data set, for example, with missing values, will have a lot of these repairs, right? Okay, so using this idea of possible repairs. So this is like, I'm going to call all the set as possible repairs, right? These are my possible repairs. Of course, as I said, most of them are not accurate. Most of them not correct. Probably only one of them is the correct one. But I'm going to call this huge set, which could be infinite set of possible repairs. Okay, now I'm going to propose a concept called certain models, which is a model that's optimal over all these possible repairs, right? So if I have a raw data, or my original data set, Let's assume that I'm going to create this set of all possible repairs for this raw data. These are all possible repairs to my data set. It's a huge data set, basically, usually. If I have enough time to train a model over every repair, and all those models are actually the same model, right? If all those models, every single one of them, are all exactly giving me the same output, the same model, then I don't need to repair, right? I'm going to call that a certain model, right? This is sort of that, oh, sorry. Okay. So I'm going to learn these models over that. And let's assume that they all learn the same model. I'm going to call that the certain model. That's an optimal model because no matter how I change my data, no matter how I repair my data, I'm going to get the same answer, right? So this is a case that I don't really need to repair my data. I don't really need to ask an expert to come in and repair my data because even a random repair will be sufficient, right? But it's quite challenging to do this checking, right? Because in this definition, this setting, I have to sort of materialize all the repairs one by one, and then train my model over single one of them, and then check the quality of all these equality of these trained models, right? So it really, this way is not an efficient way of finding certain model. So what we're going to do is try to design efficient algorithms that without actually materializing all the set of possible repairs and computing and training all the possible models can tell us whether a certain model exists or not and can learn a certain model, right? So this is a definition of certain model. I'm going to that's sort of the model that gives me the minimum loss over all possible repairs. I'm going to go over that. Okay. So what we have done, that we have designed efficient algorithms actually can do that. We have shown that it's possible to efficiently check and learn certain models for a wide variety of models. Linear regression, linear support vector machines with kernel, neural network, and all that. So I'm not going to go into details of those algorithms. You can find the proof of correctness of those in our papers. The next step is, okay, we know now that certain models exist in some cases, right? But the condition of having a certain model is pretty strict, right? It requires us to have the same answer, the same model train for every single possible repair of our data, right? It might not always happen, right? So what we have done is we have relaxed that concept and introduced another concept of approximately certain models. And approximately certain models, we say, okay, let's again do the same thing. We're going to go over sort of all possible repairs. And for each repair, we learn a model training. That's a definition, almost the same definition. And let's assume we learn a model, an optimal model over each possible repair, right? If I can't find a model that's not exactly the same as all these are could be different this time. The optimal model could be different. But if I can find a model that's sufficiently close to all of them, that could be okay for many applications. So very, very close to, so in terms of loss function. That's what I call approximately certain model. So it doesn't require all these models, each trained on a separate possible repair to be exactly the same model. It says, well, I mean, if you can find a model that's very close with some threshold of epsilon, for example, it's very close to these models, then it would be quite accurate, right? I can just use that again without cleaning my data set, right? I'm going to lose a bit of performance, right? But it may worth it in many applications and in domains because it may save a lot of resources and time. So again, we have kind of the same definition here. That's sort of an optimal. That's kind of that model is quite similar in terms of a loss function, quite close to every single possible repair. We also have, of course, we have the same problem, algorithmic challenges here, right? If I want to find an approximately certain model this way by materializing every single possible repair, and then learning a model over every single possible repair, and then checking if they are close to each other or if there's a model that's close to everybody, that will take a lot of resources. I mean, that often is not possible to do with finite amount of resources that we usually have. So the goal is to then design efficient algorithms that without actually materializing these, creating these sort of possible repairs and training the models over every single one of them can tell me, without doing those, whether I have an approximately certain model in my setting and learn it, right? And that's what we have done. So we have proposed algorithms that for all ML models with convex loss functions, like logistic regression, support vector machine, linear regression, efficient algorithms that can tell us whether approximately certain models exist in our setting and learn it. So next step. So far, we have been able to actually find out cases where we can learn directly over their data without doing any training. Sometimes without losing any performance in theory, and sometimes losing just a bit of performance in approximately certain models. But there could be cases where we neither have certain models nor approximately certain models, right? So what to do then? So the next natural question will be, well, now, can we learn ML models in those settings where we don't have a certain model or approximately certain model with minimal repairing efforts, right? Instead of repairing the entire data set, just repair repairing the entire sort of all these data items, erroneous data items, I can just repair 1% of those, something like that. So then that would be the other proposal, right? So we get the raw training data, we check if the dirty data is influential or not. If it's not influential, okay, we go with certain model, approximately certain model to learn. If they are influential, then we try to find a minimal subset to repair, right? And then finally learn the accurate model. Okay, so again, I'm going to use the same sort of idea of a set of possible repair from my data set to define this minimal repair. So that what I call as minimal repair is the minimal subset of data that I can repair in order to get a certain model. So more precisely, let's say I have a raw data coming in. I like to repair a very small subset of that, like incomplete samples. Here I have null values, I have missing data here. I like to repair those in a way that if I go over all possible repairs after repairing that subset. If I materialize and produce all possible repair from my data, right? Then I'm going to have a certain model, right? So this example, in this example, if I fix this missing value, if I impute this missing value for Portland, right? I will have a lot of possible repairs where I put some arbitrary value to the missing temperature of San Francisco, right? But still, I'm going to have a certain model. So essentially, a minimal repair is a subset data that if I repair that, I'm going to have a certain model, right? That would definition my definition of minimal repair. Now, of course, if I have a certain model, then I really don't need to repair San Francisco. I don't need to repair the rest of the data because I'm sure I'm going to get one model no matter how I repair my data. Unfortunately, it's very challenging to find this minimal repair. So you can prove for SVM and verification the problem was NP-hard. So what we have done then, we have proposed efficient approximation algorithms to finding minimal repair. So they're going to give me these algorithms. They're efficient, but they're going to give me a bit more than I need. So I need to essentially over-impute or over-clean a bit or under-clean a bit. So they give me just an approximation. So we have proved the error bounds of our algorithms, and you can find it in our papers. So they have guaranteed error bounds. for linear regression and linear support vector machine. So similar to the previous case when we said, okay, we have certain models and then we defined approximately certain models because certain models were just too strict. We do the same thing with repair, right? So instead of trying to repair a subset data, so we have a certain model, we can do the same thing with the approximate certain model. I mean, repairing a subset data. So after repairing that subset, I'm going to have an approximately certain model, right? And that might be more flexible because approximate model it has a sort of a more relaxed condition. So probably then I'll be able to repair smaller amount of data compared to the minimal repair. That's what we call almost minimal repair. So even smaller than minimal repair. And we have, again, algorithmically, it's also very challenging. It's also NP hard because the minimal repair is NP hard. And again, algorithmic is challenging because then you have to materialize, so go over all the subsets of data, figure out if you repair them, then you materialize all possible repairs for that partially repaired data set, and then check if asym exists. So it's algorithmically challenging to do it this way. So fortunately, we have been able to propose efficient approximation algorithms to finding approximately almost minimal repair for all ML models with convex loss functions, right? And we have shown that these algorithms don't over approximate, right? I mean, they don't really give me the larger set that I'm supposed to repair. So I'm not going to go over the details of the algorithms that we have. I'm going to go to the sort of our empirical evaluations. We have done empirical evaluation using real world data, synthetic data. These are some of the real world data that we have used with different missing factor, different missingness type, different number of features, number of training samples, different task classification, regression. And we have compared our method to some baselines. No imputation, we just don't impute, don't repair, you just delete the dirty samples. Then various imputation techniques from diffusion-based to missing forest, mice, well-known ones, on-demand cleaning, and then our approaches, right? And the comparison is should based on the imputation cost, number of samples we need to repair, because in many domains, we still need to use experts. So it's important to reduce their work and to repair the data. And also the learning and imputation time. And so these are the cases. So for these two data sets, for example, so we have sort of NFL and COVID. Basically here, the minimal repair, sorry. A minimal repair exists, and we can sort of figure that out and save a lot of time of imputation or on-demand cleaning with a small amount of overhead. So we don't really have much overhead for actually running our algorithms and returning accurate results, right? Oops, sorry. And the same thing goes for approximately certain models, right? So we are able to save a lot of cleaning costs from like 15,000 samples to nothing, or 300 samples to nothing. And also with the small computational overhead and nice quality performance. And even when approximately certain models or certain models don't exist, then we can argue that just checking that will checking whether certain model or approximate models exist will put a small really overhead in terms of time. In a matter of seconds, you can check that. Really, doesn't have much overhead. Next, I'm going to just go over parts of these results for SVM. That's minimal repair, approximate, and almost minimal repair. You see here in terms of samples imputed. So instead of 100% as a baseline for this dataset, breast cancer dataset, in minimal repair, we get to 18%. We just need to repair 18%. And then for almost minimal repair, we have like around 1%, 1.3%, while on demand is 87% still. And it also saves time, for example, if you use an imputation model like TCSDI, which is sort of a diffusion-based one from 100 seconds to just 3 seconds, 4 seconds. So in conclusion, we propose certain model approximate models to learn accurate models, do accurate learning directly over daily data without any cleaning. And we have done it for a wide variety of models. And when we don't have certain models or approximate models, we can actually use those ideas to find the minimal subset data to clean, to repair. And we have shown that these approaches work quite well on real-world data sets. For more information, you can find more information, the source code, data set, all that in our project page. I'll be happy to answer questions.
Thank you so much. That's very interesting. I'll start with the first question. So in what settings do you see this being the most useful? Are there certain numbers of errors after which you feel like you need to do repairs? Or are there key characteristics that you should look for to understand if the data set may be well suited for these approaches?
I mean, in settings where you have a lot of erroneous data or the task is quite sensitive, that's very important to avoid. The cleaning cost is usually higher than other settings, like in medical domains, usually, because you have to actually use experts to do cleaning. And that would be great if you can figure out before asking the expensive experts to clean the data, whether you actually need to ask them, right? Or by doing minimal repair, you can usually reduce the amount of time they have to spend to repair, essentially. I don't know if I answered the question.
Yeah, I think that answers a part of it. I think I'm also wondering if there are characteristics of the data set that you can look for. Let's say if there's more than 5% of the samples that have errors, does that start to indicate that maybe this isn't the approach to use, or there's a small
No,
group of
it's not. Yeah, it's not. It's not actually. Yeah, that's a very good question. It's not. That's why the problem isn't hard, right? Because there are dependencies sometimes in data set. I mean, it depends on which samples are the most influential ones, right? For example, for SVM will be sort of these boundary samples, right? So it's really hard. You can find these sort of extreme cases with changing only one sample, and there is one sample with missing value, for example, and you have to change it because that seems to be in the boundary decision, right? So I think it depends a lot in the data. We cannot just simply say, because I don't have that many missing values or daily samples, I really don't need to necessarily train. Uh, in theory, and also I think in practice, it won't be a reliable way of judging that. It's hard to, and as I said, that's one of the reasons that problem is quite challenging to solve. It just depends on the type of model, the interdependencies between samples, the position of that sample, the daily sample in your data.
That makes sense. There's a question asking, is this approach similar to bootstrapping methods?
No, I don't think so. So the concept is quite different. I don't think bootstrapping uses sort of the set of possible repairs necessarily. There are similarities in a sense that you're also trying to do something with multiple instances, but the similarity stops there. But there are similarities in that sense, because the main difference is we are trying not to do that, right? Because the sub possible repairs is just too many, and we're trying to not to materialize them and learn over every single one of them, right? Because there are usually there are infinitely many possible repairs for a data set, for a daily data set. So we try not to do that, and we just predict that from your loss function and the properties of the data set itself without materializing those repairs.